So in this question, we are asked to solve for the function u given this pure time differential equation. And here we're given that t is greater than 0. And this is important. The reason this is important is because when we're given a differential equation, if there's any point at which it is not continuous or it has discontinuities, if the original equation has discontinuities, our differential equation isn't valid beyond those discontinuities. It's only valid within. So for here, we're going to see that we have a discontinuity in this function at t equals 0. And because our initial condition for u is given t equals 1, or a positive value of t, this differential equation that we're solving for, the equation u that we solve for, is only valid when t is positive, and they tell us that. But to start, we take the integral du by dt, the antiderivative of u with respect to t, which is equal to the antiderivative of t to the 1/2 plus 2t to the minus 1/2 with respect to t. And again, this is us calculating the antiderivative. So this is t to the 3/2 divided by 3/2 plus 2t to the 1/2 divided by 1/2 plus c. And this is what u of t is equal to. And we can see that we don't know what that constant is. And we use the initial value to solve that constant. So u of 1 equals 2/3, 1 to the power 3/2, plus 4, 1 to the power 1/2, plus c, and we're told that this is equal to 5. So with this being the case, we then simplify what we have. 2/3 plus 4 plus c equals 5. So c equals 5 minus 4 minus 2/3, which equals 1 minus 2/3. So c equals 3/3 minus 2/3 equals 1/3. And from here we can see that u of t equals 2/3 t to the 3/2 plus 4t to the 1/2 plus 1/3. And we have our function for resume recording, and we're going to carry on with our next question. So in this example, we are given a logistic equation, and we're asked to solve for two things. One, equilibrium. And two, stability. So to solve for equilibrium, in order to solve for stability, we first need to know our equilibrium. So the first thing that we're going to do is calculate our equilibrium points. Then we're going to calculate stability. To calculate equilibrium points, what we're going to do is we're going to take this expression and replace everything with x. Everything with xn, or xn plus 1, or xn minus 1. All our xn terms are going to be replaced with x bar or x hat. So we have x bar equals 4/5 x bar 1 minus x bar. Then what we're going to do is we're going to solve for x bar. And to do this, what we do is we factor. We bring everything to one side and factor. So 0 equals 4 over 5 x bar 1 minus x bar minus x. So 0 is equal to x bar 4 by 5 times 1 minus x bar minus 1. So 0 equals x bar times 4 by 5 minus 1 minus 4x by 5. 0 equals x bar minus 1/5 minus 4x by 5. So 0 equals x bar over 5 or minus 5, 1 plus 4x. So from here we get that x equals 0 and x equals minus 1 over 4. So those are our two equilibrium points, x equaling 0 and x equaling 1 over 4. And when we solve the equilibrium points of our difference equations or recursive relations, it's the same process every time. Now what we need to do is we need to determine if it's stable. And in order to determine it's stable, we use one of two ideas for stability or instability, I should say. If the absolute value of f, the derivative of f of x bar, is less than 0, then we're stable. If the absolute value of the derivative at x bar is greater than 1, then we're unstable. I'm a little rocky right now because the train's moving around. So let's just try that again. Not stable or unstable. Unstable. So, but the big question that I always asked, or I always struggled with, was what is my f of x? And it turns out that f of x is the equation here. It's the xn plus 1 is equal to a function of xn. And that function is my xn. So in this case, my f of x is equal to 4 over 5 x 1 minus x. And this is my function. So now what we're going to do is we're going to look at trying to compute the derivative of the function. And this is where I say to a lot of people, instead of jumping right in and trying to solve the derivative by using product rule or any method, start by making it simpler. So instead of jumping straight to it, we're going to rewrite f of x and expand this out. This equals 4 over 5 x minus 4 over 5 x squared. And now the derivative, we can see, equals 4 over 5 minus 2x. And now we're going to check this function evaluated at these points. And we can see that f prime of 0 equals 4 over 5. Therefore, the absolute value of f prime at 0 equals 4 over 5, which is less than 1. Thus, stable at x equals 0. We also have f prime of -1/4. And this equals, when we plug it in, we get 4/5 plus 1/2. And this is greater than 1. So because it's greater than 1, this tells us that we're unstable at x equals -. So to review, what are the 2 steps we did for this process? We first determined where the equilibrium were by setting x bar equal to f of x bar. And then we determine the stability of each of our roots by calculating the derivative of f at x bar and see if the absolute value is less than 1 or greater. So now we're going to look at question 16. And this asks us to estimate the area under the graph from x equals 0 to 4 using 4 approximate right angles and endpoints. So to start, what I'm